Good morning, welcome back. So today's topic is dynamic chemical equilibrium, and this is going to be fascinating to teach using a piece of paper and a dot cam, because the whole idea here, dynamic chemical equilibrium, the key idea and the thing that is most often confusing is this part right here, which means motion, moving, active, dynamic chemical equilibrium. Things are in constant motion. They do not stop. Dynamic chemical equilibrium is a state of constant change. So to teach this, usually what I do is I'm gonna describe the game for you, and maybe that'll do help a little bit. So usually what we do is we take your classroom. Here's your classroom, and y'all are sitting at desks. So these are people at desks. Man, that looks like a sad face. I was thinking these are two people sitting at a desk. I'm like, that looks even sadder now. I've not pre-planned this. Okay. But, so, and then I say, who wants to start? We need a start team. And the start team, let's just go with teams, because it's teams that are more important than sitting or not sitting. Actually, some years everybody stands. Okay, so we need two teams, and a bunch of people jump up and they're like, we want to be the start team. So here's the start team, and then there's a bunch of people. We choose a couple people for the start team. The rest of y'all are make some guesses here. We've got a start team and an end team. Okay, the start team gets all the bouncy balls. Got a whole bunch of ball pit balls, like playground balls. And when we start, so here's the start team. Here's the end team. We'll add some fancy science words to start and end of a reaction. This is all modeling a reaction here. Okay. And to start, so at the beginning moment, the start team has all the bouncy balls. So these are all bouncy balls. And the end team has none. Everything starts. And let's just add some words. In a reaction, what do you start with in a reaction? I'm forever asking my .chem questions. These are the reactants. These are the products. And we can even graph this. I'm doing this a different way than I usually do in class, but that's kind of okay. We can graph this. We can say at the beginning, so at that beginning moment, all of our stuff in our reaction, everything is reactants. I actually need two colors for this. So everything starts as reactants. So that beginning moment, our start team is going to be pink, okay? So the start team, everything starts in that starting spot, okay? And then I say go. I haven't said most of these words yet, usually in class. Just give all the bouncy balls the same side of the room, and then the reaction starts. I say go. Still got the start team over here. And without any further instruction, you all know that what I want you to do is throw bouncy balls at each other. And it often turns into a chaotic day, which is fine. Okay, so we start with all the bouncy balls on the start side, on the reactant side, and quickly all of your people start throwing the bouncy balls into the product side. And what we're modeling here is we're modeling, let's say somebody's still holding onto the ball. We're modeling that, and I say stop, and let's say your bouncy balls are there when I say stop. What we're modeling is, this is a few seconds in, that in your reaction, in your game, in your reaction, some of your reactants have become products. Your start team threw their bouncy balls to the end team. And frankly, as you're unsurprised to hear, there's an exchange of bouncy balls here. So your products start throwing their bouncy balls back to the reactants. The reactants throw their bouncy balls back to the products. And you get this dynamic shift going on, right? This is the kind of day where you put your water bottle on the floor. It's very dynamic. There's bouncy balls flying all over the classroom. And what we're modeling is that the reaction is happening constantly in both directions. So we have some of the reaction going forward. And in the forward reaction, your reactants are forming products. But once your product people have bouncy balls, they're like, hey, you just threw a bouncy ball at me. Your products tend to also throw their bouncy balls back to the reactants. And you start to see both a forward reaction, reactants turning into products, and a reverse, a backwards reaction, where the products are throwing their bouncy balls back to the reactants. And both things happen. So some reactants turn into products, throw their bouncy balls to the products. Some products turn into reactants, throw their bouncy balls back to the reactants. Many reactions are reversible. Let's write that back. This is a key idea here. Many reactions are reversible. What that means, they can go forwards and they can go backwards. And in fact, the symbol for reversible is that double arrow. So to show that a reaction is reversible, we've got a forward arrow and a backwards arrow. That symbol means reversible. Boy, I realize this went kind of fast. This may be the trickiest concept to understand from a DotCam, just because we can't model the physical nature of it very well. I'll get you videos, but I think there's a lot of value to actually physically doing it ourselves. It is very dynamic. It is in constant motion, constant change, constant motion. It does not stop. It's constantly changing. So you've got a constant forward reaction and a constant backwards reaction going on at the same time. This is the case for most chemical reactions, or many, a lot, experience the state of equilibrium. What even is equilibrium? So, oh boy, maybe I'll get there in a second. Most reactions, many are reversible. Excuse me. A lot of the ones that we're most familiar with are not reversible, which is a little bit tricky to work with that also. So some things are not reversible. For example, burning a fire, right? Not reversible. Digesting your food. You don't undigest your food. That is a one-directional reaction. Reversible reactions are, we tend to go to the lab. I should get you some lab videos of labs of reversible. Maybe that's how we're going to do this. I'll get you some lab videos of reversible reactions. We almost always do this in our acid-base unit also, which is really fun because you can see the forward and reverse reactions in real time in front of you. You can see it change. And you can see that you can drive it forward or drive it backward. Basically, if you want to form something, you can drive a reaction towards the direction that you want it to go. Great, yeah. I'll get you videos of reversible reactions because there's tons of them. Most solution chemistry is reversible, and most chemistry is solution chemistry. Like ocean systems, but it's like a little bit harder to imagine. I don't know, I mean, like, this is really broad, but like your body temperature is in a state of dynamic equilibrium. You get cold, your body shivers, or even if it doesn't shiver, it like your body does things to keep you warmer when you're cold, because you want to stay, you want to maintain a constant temperature. That's what you want. So your body dynamically responds to the conditions around you. Even if you're just a little bit chilly, you're going to metabolize a little bit more, get a little bit more warmth. If you're a little bit warm, you might open up your blood vessels near the surface of your skin. This is going deep into biology. But it's a dynamic process because you can take yourself to different temperatures and live. Thanks, body. And essentially it's your body responding to the temperature around you. If you put yourself somewhere cold, your body responds by making you warm. If you put yourself somewhere warm, your body responds by getting you a little bit cooler. So it is the state of constant change. Another example, another whole set of examples, dance, or walking, or sitting on your chair. These are all states of dynamic equilibrium. These are states of dynamic physical equilibrium instead of chemical. But physical equilibrium is really interesting also. Here's another physical equilibrium that you can do right here, right now, in the comfort of your own home. But balance your pencil, or whatever your writing utensil is, on your finger. At this point, your pencil is falling equally in the forwards direction. So think of those little arrows there. Your pencil is falling in the forwards direction at the same rate that it is falling in the reverse direction. It's dynamic. You can move this around, right? And you can shift your equilibrium if it completely falls. And I should go with it. Once your pencil falls, this is a new state of equilibrium. Except that my pencil is actually moving here. Let's just do that. Okay, so now it's on the table. This is a new state of equilibrium. This is a more, forgetting the word stable, essentially, state of equilibrium. Like, it's really unlikely to fall further from here, although we could push it off the edge of the desk and it would find a new equilibrium on the floor. You can practice dynamic equilibrium from trying to get your pencil to balance on your hand. I'll hand out meter sticks and have people balance the meter sticks on their hands. Anytime that something's falling equally in all directions, if, I just got ahead of myself. If the rate forwards is equal to the rate backwards, that is equilibrium. So it's still motion, there's still stuff going on there. But if the rate forwards equals the rate backwards, that is equilibrium. Let's actually write that down. I'm going to write that down here. So we got this idea that the law of reactions, we'll come back to that graph. Okay, so you started your graph, we will come back to it. That a lot of reactions both go forwards and backwards. And equilibrium is if the rate forwards equals the rate backwards, that is equilibrium. So the thing that's equal, what's equal? You see the word equal inside of equilibrium, right? So what is it that's equal? What's equal? The rate forwards equals the rate backwards. Again, this may be the trickiest thing to understand virtually. In part because something seems constant. From our macro level, falling forwards at the same rate that you fall backwards can appear constant. But balance your pencil on your finger and then figure out what it is. I can't do it anymore, that's weird. What it is that appears, that is constant. And you're going to balance your pencil before me. And what you're going to see is that it's the amount of pencil on the two sides of your balance point. That's what's going to remain constant. It's still falling. As we know, it's really easy to make this still fall. At this point of equilibrium where it's falling forwards at the same rate that it's falling backwards, it's still dynamic. What remains constant is the amount of stuff you have on each side. So from our macro level just means like big. So you're a human, you're a big thing. We'll think of using like particle level goggles to see these reactions, to see these things changing. In your game in the classroom, each of these bouncy balls is a particle. So you have to zoom into the particle level to see the change. It's totally happening. You have a constant reaction forward and a constant reaction backwards. But if we zoom out and take this over time, so let's say macro level means zoom out, or look at this over a lot of time, and what you see is the amount of product and amount of reactant stay more or less constant. Kind of like your pencil. Like your so when we play this game, I stop you a few seconds in, we count the bouncy balls, we make a ratio of bouncy balls on the reactant side to bouncy balls on the product side. I say go, you play the game, bouncy balls are flying around the classroom. A few minutes in, I say stop. Sometimes we go again, a few more minutes in. And you start to see something constant, which is that even though every time I say go, you're throwing balls at each other, every time I say stop, what's constant is that ratio of bouncy balls on the reactant side versus bouncy balls on the product side. Particles, right, in our reaction, particles in reactant form compared to particles in product form. Let's do that graph, because we never actually finished the graph. At that beginning moment, you had a bunch of reactants, but no products. And in those first few, just very initial second, like moments, not even seconds. Seconds are longer than people think they are. But in those first moments, you had a noticeable decrease in reactants, because all your reactant people threw their bouncy balls to the products. Right away, the amount of reactants dropped. At the same time, the product people are getting bouncy balls thrown at them. At that moment, there's a noticeable increase in products, because now you've got like bouncy balls being thrown at your product people. Oh, these are always nice little curves. I'm not an art major. And then, so this is time. This is amount and time. Our reactants are still pink. Our products are still green. So in those first few moments, and time doesn't work like that. So like, let's say we've stopped at that time. In those first initial moments, your amount of reactants dropped a whole bunch because your reactant team, when I said go, they were like, man, we've got all the bouncy balls. And they threw them all to the products. In that first moment of the reaction, you get kind of usually really fast reaction because it has the conditions to go, so it goes. And same thing with products. You start with no bouncy balls in the products team. When you start your reaction, it's all reactants. But in that first little bit of time, and you notice that this is not an amount, reactions go at different rates, like we learned yesterday. It's not that everything goes at the same rate, but everything starts as reactants, forms products initially. So we get an initial growth of products, and then over time, we pause the game a few seconds in, it looks like this. I say go, you're throwing balls at each other. A minute or so in, I say stop. We count how many of each, and I sometimes rig this, but it's what kind of we observe in a lot of reactions. Even a further time in, you've got the same ratio of reactants to products. I say go, you chuck balls at each other for a while. I say stop, we take another picture. This is how you like kind of really do it in the lab also. Like you take a little pipette, you take like a drop or something of the reaction out at a certain moment of time and assay it, figuring out what is in it at that time, and then put little dots on your graph, just like we're doing right here. You can't actually stop your, I mean you can, but it's hard to stop your reaction. But with the bouncy balls, you can, anytime I say go, you throw them at each other. And we could do the same thing later. Say stop, look at the concentrations, look at how much you have. You still have a similar ratio of products to reactants. And so things that are staying constant is the amount of reactant stays constant over time, the amount of product stays constant over time. That ratio, amount of product to amount of reactant, that ratio stays constant over time. The actual reaction is still happening. You can't actually say go and stop to a reaction. Like, it's essentially throwing bouncy balls at each other constantly. Reactants forming products forming reactants at this constant exchange. That's the dynamic part. was something else I was going to say. Yeah. So the reaction is still happening. It's dynamic. It never stops. If the rate forward is equal to the rate backward, that is what we call equilibrium. And at equilibrium, what stays constant is the amount of product, the amount of reactant, and that ratio stays constant. This is what I was going to say. You will notice that the amount of product does not equal the amount of reactant. Every once in a while it does, but usually it does not. Usually at equilibrium, your reaction has either more product or more reactant. What's equal is the rate forward equals the rate backwards. So how fast the reactants are throwing bouncy balls to the products equals how fast the products are throwing bouncy balls to the reactants. I'm going to make sure that I covered all your questions, just like yesterday. First of all, what is equal? Why? What does it dynamic mean? Real life example. Yeah, you can use the pencils. I'll post some more videos also. Great. So you're going to do number 1 through 6 on your chemical equilibrium concept page. I'll get you the math tomorrow. I'm going to do the full thing. I usually do the full answer key. I think I forgot today. So here's all the notes from today. Feel free to ask your questions. This may be the trickiest day of the whole quarter, conceptually. TED Talk is great. Here's the videos I'm going to give you. I'm going to give you a TED Talk, some labs, and another example of equilibrium. I play this every year and it's silly, just kind of this, this whole equilibrium concept day is silly. Yeah, I'll give you another silly video that's another model of equilibrium. So something where the rate forwards is equal to the rate backwards. It's in constant motion, constant change. And from the macro level, the screen angle of the video stays constant, right? So even though everyone in this video is in constant motion, their rate forwards is more or less equal to their rate backwards. It's a silly video. I'll share it with you also. All right, enjoy.